Okay, so in this video what we want to do is we want to look at the distribution of the sample proportion. So if we were to take lots and lots of samples and calculate the sample proportion for each one of those samples, what's going on? Or I guess the thing is, what is the probability of selecting a sample with a particular sample proportion is what we want to look at. So let's consider the following collection of black and white balls. Okay, so this picture over here. And we're going to take that as our population. Now, obviously it's a very small population, but this is so that we can actually see what's happening with the numbers. So for this sample, the collection is the population. This collection of balls is the population. So the population size is 15, you can count them up. And the population proportion of white balls is 6 out of those 15 balls. Okay, so the population proportion is 2/5 or 0.4. So normally we wouldn't know the population proportion. And so what we would be doing is choosing a sample from the population and calculating the sample proportion. And in this case, we're going to look at a sample of size 5. So lowercase n is 5. Okay, so one of the issues with this is obviously we could choose samples such as those below. So it would be perfectly possible that we could end up with a sample that contains 0 white balls, or that contains 1 white ball, hence the population the sample proportion is 1/5, or 2 white balls, 2/5, and this one would match the population proportion, but it's not going to happen all the time. Or we could choose 3 white balls, a sample with 4 white balls, or a sample with 5 white balls. So it is possible that our sample proportion could be 0, 1/5, 2/5, 3/5, 4/5, or 1. Okay. So it is possible that using a sample won't give a good representation of the population. And so for this example, let's consider the likelihood that we actually select a sample such that the sample proportion is the same as the population proportion. Now, if the sample proportion is to match the population proportion, then my sample needs to comprise 2 white marbles and 3 black marbles. And I can calculate the likelihood of this selection using combinatorics. Okay, so the number of ways of selecting 5 balls from 15 balls. So the number of possible selections that I could make, imagining that the balls are all numbered, so that even if this is ball number 1, 2, 3, 4, 5, and this is 6, choosing 1, 2, 3, 4, and 5 is different from choosing 1, 2, 3, 4, and 6. Okay, so that would be considered a different one, even though it's still 5 black balls. Okay, so the number of ways of choosing 5 balls from 15 balls is 3003. Okay, so our combinatorics, menu 5 for probability, 3 for combinations. We've done 15, choose 5. You can confirm there that it's 3003. Okay. The number of ways of selecting 2 white balls from 6 white balls. So we want to, out of the 6 white balls available, we want to choose 2 of them so that our sample matches the population proportion. So it'll be 6, choose 2. So menu 5, 3, 6, choose 2. You can confirm is 15. The number of ways of selecting 3 black balls from the 9 black balls. So 9, choose 3. Okay. And then the number of ways of selecting 2 white balls and 3 black balls. When we use the word and, we're multiplying. It's going to be that times that. So we want to choose 2 white balls from the 6 white balls and choose 3 black balls from the 9 black balls. That is 1260. And so therefore the probability of selecting 2 white balls and 3 black balls from 15 balls is this divided by this. Okay. Now there's actually a slight error there, sorry, that should have been 15, choose 5. So it's going to be 1260 divided by 3003, which is 60 over 143, just as a rough estimate, about 0.4. So we've got a 40% chance, roughly speaking, that our the sample we select will have a sample proportion that matches the population proportion. Okay, so that means there's a 60% chance that it won't, and so therefore our sample won't actually be a good inference for the population. It won't be able to be easily inferred. Okay, so we've now established that the probability of p hat equaling p, so the sample proportion equaling the population proportion, so that is for this problem, the sample proportion equaling 2/5, is 60 out of 143, so about 40% or 42%. So this leads us now to think about random variables and probability distributions. So previously we would have considered this situation by defining the discrete random variable x as follows. So if x is the number of white balls in a sample of 5 balls, then x is equal to, x could either be 0, 1, 2, 3, 4, or 5. Okay, it would be possible to select 0 white balls, 1 white ball, 2 white balls, 3 white balls, 4 white balls, or 5 white balls out of my sample. And so we can form the probability distribution here. Okay, so this was the one that we already calculated. The probability that I select 2 white balls we worked out was 60 out of 143, and we can calculate these other values in the same way. So for example, the probability of selecting 1 white ball would be menu 5,3. So from the, how many white balls were there again? 6 white balls. So from the 6 white balls we want to choose 1. There's one way to do that. Menu 5,3. From the remaining 9 black balls we want to choose 4, so that we have a sample of 5. There's 126 ways of doing that. So the number of ways of choosing 1 white ball and 1 black ball is 756, and therefore as a probability it's 756 out of those 3003 possible selections, 36 out of 143. Okay, so that's how we've calculated all those values in that table. So we have this probability distribution now for the number of white balls in a sample of 5 balls. Okay, but now we're more interested in setting this up as a distribution of the sample proportions. So we define the discrete random variable p hat, where p hat is x, the number of white balls in the sample, divided by n, the size of the sample. Okay, so if there are 2 white balls in the sample, that's a proportion of 2/5. If there are 4 white balls in the sample, that's a proportion of 4/5. So we're dividing our x values by n, lowercase n. So the probability distribution of p hat is as follows. So p hat is the proportion of white balls in a sample of 5 balls. The possible values of p hat are 0, 1/5, 2/5, 3/5, 4/5, or 1. So we set up our probability distribution with all of those options for p hat and the probabilities corresponding to each of those, which are the same as the probabilities that correspond to x equals 0, 1, 2, 3, 4, or 5. Okay. Okay, so this distribution for p hat is called a sampling distribution. And we can calculate the mean or expected value of the sample proportion in the same way that we calculate the mean for any discrete probability distribution. 0 times this, 1/5 times this, 2/5 times this, plus 3/5 times this, plus 4/5 times this, plus 1 times this. And we find when we do that calculation is written out here, we get that the expected value of p hat, the expected value of the sample proportion, on average the sample proportion is 2/5, which we know is p. Okay. And so this is getting us to this idea that if the expected value gives the population proportion, then if we were to take lots and lots of samples, we should be able to get close to the population proportion on average. So on average, we expect the sample proportion to equal the population proportion, which means that if we were to take lots of samples, as I just said, we should be able to make accurate predictions about the population. In this example, the probabilities involved with the selection of each sample have been dependent. So for example, if I'm selecting 5 balls from a bag of 15 balls, the probability of selecting a white ball changes each time I select one of those 5 balls, okay, which is why we've done them as a selection. So for example, the probability of me choosing a white ball out of the 15 balls is 1/15, but then the probability of me choosing a white ball at the next selection, if I've already chosen a white ball, would now, sorry, it's not 1/15, there were 6 white balls, 6/15. But then the probability of me choosing another white ball becomes 5/14. Okay, so that's one of the issues. But when we have situations where the selections in the sample involve independent probabilities, then we can use a binomial distribution to generate this probability distribution, and it's actually going to be a lot more efficient. So sampling from a large proportion. So when we sample from a large proportion, or a large population I should say, we assume that the probability of observing the attribute we're interested in remains constant with each selection. Technically it doesn't, but if we've got a large enough population, for all intents and purposes it is, we can assume it's constant. So for example, if our original sample had been 15,000 balls, comprising 9,000 black balls and 6,000 white balls, then we could assume that the probability of selecting a white ball remains constant at 2/5 or 0.4. Technically, the probability of the first ball being selected as white was 6,000 divided by 15,000, which is exactly 0.4. And then the probability of the second ball also being selected as white is 5,999 divided by 14,999, which is 0.39996. So close enough to 0.4. So when the population is large enough, we can treat the probabilities as being independent, and therefore we can use a binomial distribution. Similarly, sometimes we have statistics that we know are, again, for a large enough proportion. So, for example, if we're told that 70% of all 17-year-old Australians attend school, then that's a parameter for a large population, and we could therefore safely assume that in collecting the random sample, there's a constant probability of 0.7 that each 17-year-old being selected attends school, okay, because the population, is large enough. So if a random sample of size n is selected from a large population, in which the population proportion is p, then we can assume that the sample proportion is of this form. Well, we can assume this all the time, but the important thing is that then we can assume that we can use a binomial distribution. So we can assume that p hat is x over n, where x is a binomial variable. X is the number of elements in the sample with the attribute of interest, and x is a binomially distributed variable such that x is distributed binomially, where n is the sample size and p is the population proportion. So this means that the expected value of x is np, because it's a binomial variable, we know that, and the variance of x is np times 1 minus p. And so we can calculate that, because we know the expected value of p hat is the expected value of, we've got this connection, x over n, and remember, we have these properties for expected value of ax plus b is a times the expected value of x plus b. Okay, so if our a value is 1 on n, what we essentially have here is the expected value of 1 on n times x. And so that is 1 on n times the expected value of x, which is what's happening here. And so the expected value of p hat is 1 on n times the expected value of x. We know from our binomial distribution that the expected value of x is np, and so therefore the expected value of p hat is p. So that wasn't just a coincidence in the previous example. In a distribution of the sample proportions, the expected value will be the population proportion. Similarly, the variance of p hat, we know, generally speaking, that the variance of ax plus b is a squared times the variance of x. Okay, so if we're looking at here the variance of 1 on n times x, then that's going to be equal to 1 on n squared times the variance of x, okay, which is what we've got here. So therefore we've got 1 on n squared times np times 1 minus p, and so that n will cancel with one of those n's, and we've got p times 1 minus p over n is the variance, and therefore the square root of that is the standard deviation. Okay, so if a random sample of size n is selected from a large population, then the mean and the standard deviation of the sample proportion are given by p, and the mean is p, and the standard deviation is the square root of p times 1 minus p over n. And we call the standard deviation of the sample proportion the sample error. Okay, so we can now use our binomial distribution and we can calculate mean and standard deviation of the sample statistic. Okay, so let's have a look at this. Suppose that 20% of Australian children learn an instrument. A random sample of 4 students is selected. If x is the number of children in the sample who learn a musical instrument, state the possible values of x. So, possible values of x, if we're taking a sample of 4 students, it might be the case that none of them learn a musical instrument, 1 might, 2 might, 3 might, or all 4 might. So those are the possible values of x. And then if p hat is the proportion of children in the sample who learn a musical instrument, state the possible values of p hat. Okay, so p hat could be, now if no children in the sample learn a musical instrument, then the proportion is 0 out of 4, so that's still 0. If one child learns a musical instrument, that's 1 out of 4, which is a proportion of a quarter. 2 quarters, which is half. 3 quarters, or 4 out of 4, which is a proportion of 1. Okay, so those are the possible values for our sample proportion. So construct a probability table to represent the sampling distribution of the sample proportion of children who learn a musical instrument in the sample. Okay, so we want p hat. Let's try again. Okay, and then we want the probability that p hat equals p hat. Remember, that's an uppercase p and then a lowercase p. It's a bit hard with p. Okay, and we know that there is 5 possibilities. 1, 2, 3, 4. Let me just make that a bit bigger. 5. Okay, we know that p hat could be 0, 1 quarter, 1 half, 3 quarters, 1. Now, p hat is not the binomial variable. X is the binomial variable. X is a binomial variable where n is 4 and p is 0.2. That's how 20% of children learn a musical instrument. So therefore, we can work out the probability. So this probability here, the probability that p hat is equal to 0 is the same as the probability that x is equal to 0. So we can use our binomial distribution for that. So menu 5, 5, and we could do binomial Pdf because we just want one particular value. Our number of trials is 4, our probability of success is 0.2, and our x value is 0 in this instance. And so that gives a probability, I'm just going to check that accuracy because I think that's exact, yeah, of 0.4096. Remember, we could also work that out using our binomial rule, so it's going to be 4 choose 0, p to the power of 0, so p in this case is 0.2, 0.2 to the power of 0 times 0.8 to the power of 4, so essentially it's just 0.8 to the power of 4, oops, sorry, 0.8 to the power of 4, sorry, that cursor's in the way there we go, so it's the same thing. Alright, and so then similarly, if we want the probability that p hat is equal to a quarter, which is what we're calculating here, probability that p hat equals a quarter, that is the same as the probability that x equals 1. We get a proportion of a quarter if the number of students in the sample learning the instrument is 1. And so that is 4 choose 1 times 0.2 to the 1 times 0.8 to the 3. Okay, so we can either use our binomial Pdf, menu 55a, n is 4, p is 0.2, and our x value in this case is 1. That's again 0.4096, or we can calculate 4 choose 1, which is 4 times 0.2 times 0.8 cubed, which is 0.4096. Okay, so either way. Now remember, when we're doing our binomial distribution, if we actually do menu 55, binomial Pdf is A, put in n and p, and leave the x value optional, leave the x value blank where it says optional, we'll get the full set of probabilities. Okay, so this is 0.1536, this is 0.0256, and this is 0.0016. Just going to see if that shows me. Yep, that's okay. Alright, again, the limitation of Binom Pdf is that it only gives decimal values, so you might have preferred to calculate this as 4 choose 2, 0.2 to the 2, 0.8 to the 2, but, oh sorry, I didn't mean that, menu 5, 3, so if we've done 4 choose 2 times 0.2 squared times 0.8 squared, we do indeed get 0.1536. So, however, if they're rounded decimals, you might prefer to, as I said, use that binomial rule. Okay, so construct a probability distribution table to represent the sampling distribution of the sample proportion of children who learn a musical instrument in the sample. I know that's a very convoluted sentence, but that is how it will be phrased. And so there is our probability distribution for the sample proportion. Calculate the expected value and the standard deviation of the sample proportion p. So we already know that the expected value of p hat is p. So we don't need to go through this whole process of, this times this plus this times this. Okay, so we already know expected value of the sample proportion is p, and the population proportion in this case is 20%. So that is 0.2. And we also know that the standard deviation of p hat, let's go back up there to get that rule, it's the square root of, so here it is here, p times 1 minus p divided by n. So for this problem, that is the square root of p is 0.2, so therefore 1 minus p is 0.8 divided by n, which is 4. Alright, so let me calculate that. Square root of, control divide, 0.2 times 0.8 over 4, and that is 0.2. So just unusual that it is 0.2, 20%. It's not deliberate that the expected value and the standard deviation are the same in this particular instance. It's just a particular product of these numbers. Okay, then we want to calculate the probability that p hat is less than or equal to 0.5, okay, which is simply using our probability distribution like we've been doing already throughout probability. So 0.5 is this one. That's the probability that p equals 0.5, and so therefore we're looking at adding up these three probabilities for p hat to be less than or equal to 0.5. Okay, so this is going to mean probability that p hat equals 0 plus the probability that p hat equals 0.25, which is a quarter, plus the probability that p hat equals 0.5, which is half. So from our table, that's 0.4096 plus 0.4096 plus 0.1536. So if we add those together, 0.4096 plus 0.4096 plus 0.1536, we have 0.9728. So the probability that the sample proportion will be less than or equal to 0.5. So the probability that the number of students learning a musical instrument in a sample of 4 will be less than or equal to 0.5, so that is the number of students would be less than or equal to 2, is 0.9728. So it is very, very likely that less than or equal to half of the sample will be learning a musical instrument. Alright, example 2. It's known that 55% of the children born in a particular hospital are male. During a particular week, 120 babies are born at the hospital, 72 of which are boys. What is the value of the sample proportion? Okay, so this is the population proportion. P is 0.55. The sample proportion, we took a sample of 120 babies in a particular week, and 72 of those were boys. So the sample proportion is 72 out of 120. 72 divided by 120, which as a fraction in simplest form is 3/5, or as a decimal is 0.6. So slightly higher sample proportion than population proportion. Find the probability that out of the next 100 births at the hospital, the proportion of males is greater than or equal to the value of p hat observed in this sample. Okay, so we need to set up a binomial variable here. So so first of all, which way am I going to do it? Yeah. So x is the number of males born out of next 100 births. Okay, so therefore x could be 0 to 100. Okay. P hat is the proportion of males born out of the next 100 births. So that could be anything from 0 to 1. Okay. Where we obviously know that p hat is x divided by 100. Okay. So we want to know, find the probability that the proportion of males is greater than or equal to the value of p hat we calculated in part A. Okay. So we want to work out the probability that p hat is greater than or equal to 0.6. So that is equivalent to the probability that x is greater than or equal to, okay, so given this, so this means that x is 100 times p hat. This is the probability that x is greater than or equal to 100 times 0.6, which is 60. Okay. Now, I should have said here, x is our binomial variable. That's why we have to define it as x rather than p hat. X is the number of males born out of the next 100 births. X is binomially distributed. N is 100, and p is going to be 0.55. That's the population proportion. We know that 55% chance of a baby being born in this hospital is male. Okay, so therefore we want to know, given this binomial distribution, we want to work out this probability. We've been doing this for a long time now. So menu 55B, binomial CDF, N is 100, probability of success is 0.55, probability of a baby being born as male in this hospital is 0.55, the lower bound is 60, and therefore the upper bound is 100. And that probability, we should have been given an accuracy here, let's say to 4 decimal places. Okay, so that probability is approximately 0.1831. Part C, given that the proportion of males in the next 100 births is greater than the value of p hat found in Part A, Find the probability that the proportion is between 50% and 70%. Give your answer correct to 4 decimal places. Okay, so here we want probability that p hat is between 0.5 and 0.7, given that p hat is greater than or equal to 0.6. Okay, so we want to convert that to x, to be about x, because x is our binomial variable, and we know x is 100 times p hat. So this is the same as saying we're trying to find the probability that x is between 50 and 70, given that x is bigger than or equal to 60. Okay, so conditional probability, we need the intersection of these two things. So that is going to be the probability that x is bigger than or equal to 60 but less than 70, over the second thing, which is probability x is bigger than or equal to 60, which we've already worked out. Okay, so we're going to need to calculate that numerator. I'm just going to edit this Binomial Pdf here. So it's inclusive of 60 but not inclusive of 70, because between 50 and 70% doesn't imply that 50 and 70% are included. So I'm going to make that 69. Although we're assuming it's rounded, yeah, it's probably a little bit. I think it probably should be. I'm going to add inclusive here because I think it's a bit problematic, and I think that was the intent. So let's do that. Okay, so let's make this 70 then. So the numerator is 0.1823 over the denominator we found up there, 0.1831. So I'm going to take this value divided by this value, and we find that to 4 decimal places, 0.9958. So it is highly likely that if the proportion is bigger than or equal to 0.6, then the proportion in the sample will be somewhere between 50 and 70%. Alright, example 3, a sampling distribution for p hat has a mean of 0.12 and a standard deviation of 0.0285. Find the population proportion and the sample size. Okay, so we know that the mean, the expected value of p hat, is p. And so therefore, this means that we know that p is 0.12, because the mean is 0.12. Okay? We know that the standard deviation of p hat is the square root of p times 1 minus p over n. Okay, so we now have worked out what p is, so we can put that into this formula here. We know the standard deviation is going to be that, 0.0285, and we now know that p is 0.12, so that's 0.12 times 0.88 over n is what we're trying to find. So we're going to want to solve that equation. Let's solve 0.0285 equal to square root of 0.12 times 0.88 over, over n. That's what we're solving for. Comma n. And we find that n, obviously it's a sample size, and so it's the nearest whole number, that is, n is 130. So we must have had a sample size of 130 if the sampling distribution has a mean of 0.12 and a standard deviation of 0.0285. Part B, a sampling distribution for p hat has a standard deviation of 0.015. If the sample size was 510 and p hat is bigger than 0.5, what was the population proportion? That should be the population proportion. Correct to 2 decimal places. Okay, so we know that standard deviation of p hat is square root of p times 1 minus p over n. So this time we know what the standard deviation is. P times 1 minus p. We know what n is, 510. And we want to solve for p. That should be p is bigger than 0.5, I think. Not concentrating today. Menu 3.1. We want to solve 0.015 equal to square root of p times 1 minus p divided by 510. We want to solve that for p. And that's in there. Okay, and we know that p has to be bigger than 0.5, and so therefore p is approximately 0.8, 2 decimal places, 0.87. Since p is bigger than 0.5. Okay, so playing around with binomial distributions and converting those then to distributions about the sample proportion, and also working with these formulas for the mean and the standard deviation of a sample proportion. So exercise 17b is the work for today.